segment number 3 of chapter 1 for Chem 150. This should be our third and final segment. We left off with sig figs and calculations, and so first we're going to focus on multiplication and division. The number of significant figures in your answer is the least of the precision of the measurements. In other words, if I'm going to take 10.54 times 31.4 times 16.987, we'll basically look at how many sig figs are in each one. So we have 4, 3, and 5, and that means we'll apply 3 to our final answer. So if I run that through my calculator, I get 5,620, and I get 3 sig figs. That's going to be 5.62 times 10 to the third. Again, if I take division, 5.896 divided by 0.008, that gives me 4 sig figs divided by 1 sig fig, which means I get 1 sig fig in my final answer. So when I run that through my calculator, I get 700, and of course I'd report that as 7 times 10 to the 2. All right, let's give it a try. Give the value of the following calculation and the correct number of sig figs. Now we're going to pretend that the units all work out here. We're not going to worry about units. We're only going to be looking at sig figs. So is my final answer 1.21213? Is it 1.212? Is it 1.212132774? 1.2, or finally is it just 1? And of course we have 4 sig figs, 2 sig figs, and then 5 sig figs. So our final answer can only have 2 sig figs. That would be 1.2. All right, how about addition and subtraction? Well, here the rule's a little more complex, it feels. The answer has the same number of decimal places as the quantity with the fewest number of decimal places in the problem. So if I take 12.9753 plus 319.5 plus 4.398, I look at how many decimal places we have. So we have 4, 1, and 3. The least number of decimal places would be the 10th place, 1 decimal place. And so I'd round my answer to 336.9. For subtraction, we'd do the same thing. So 397 minus 273.15. We have 0 and then 2, and so the least of those is 0. So our final answer would be 124. All right, let's have it so that you give it a try here. For each calculation, give the answer to the correct number of sig figs. So here we're looking at addition, and I'll pause. And hopefully you got 11.3 grams. We could rewrite that as 1.13 times 10 to the 1. You don't have to rewrite that in scientific notation if you didn't want. You could have left it as 11.3. How about 19.556 degrees C minus 19.552 degrees C? Hopefully you got 0.004 degrees C. Or if we rewrite that with 1 sig fig, 4 times 10 to the negative 3. All right, how about 327.5 meters times 4.52 meters? And so hopefully you got 1.48 times 10 to the 3 meters. How about 15.985 grams divided by 24.12 milliliters? 4 sig figs, so hopefully you got 0.6627 grams per milliliter, or you could rewrite that as 6.627 times 10 to the minus 1. All right. When the expression 412.272 plus 0.00031 minus 1.00797 plus 0.000024 plus 12.8 is evaluated, in other words, if we do the calculation, your answer should be expressed as 424.06, 424.064364, 424.1, 424.064, or 424. This is exactly like Mr. Caro's multiple choices on exams. So how can we get this kind of fast? Well, we're going to be looking at decimal places, right? Because this is addition and subtraction. And so here we have 3 decimal places. We have 1, 2, 3, 4, 5 decimal places, 5 decimal places, 4, 5, 6 decimal places, or 1 decimal place. And of course that means my answer can only have 1 decimal place. So we get 424.1. All right. different values here, 152, 0.0028. Again, we'll do the calculations here, and will our answer be expressed in the tenths place, hundredths place, thousandths place, 10,000ths place, or 100,000ths place? So here we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3. So we'll get the 1, 2, 3, right? We'll get the thousandths place. So we have tenths, hundredths, thousandths place. So that would be C. All right. For the following calculation, give your answer to the correct number of sig figs. So we have 71.359 minus 71.357 divided by 3.2 times 3.67. Now here, you have to keep track of your sig figs for each type of calculation. So as we do subtraction within the parentheses here, orders of operation, we're going to be 1, 2, 3 will be in the thousandths place. Then when we do the multiplication, we get 2 sig figs. So, in other words, here we get the 0.002 because we get the thousandths place. However, when we divide, that subtraction gives us 2 sig figs, right? Because we're multiplying this by that, so we'll get 11. That means we're going to take the 0.002, 1 sig fig, divided by 2 sig figs, and so our final answer is going to be 2 times 10 to the negative 4 meters per second squared. Right, so here are the meters carried through. Here we see we multiply the seconds, we got seconds squared. Our unit becomes meters per second squared. All right. How about 13.674 times 4.35 times 0.35 divided by 856 plus 1531.1. So again, we'll take 13.67, we have 5, 3, and 2. So when we multiply this out, we get to keep 2 sig figs. Here we're doing addition. So here we have both of them in the seconds, and we have 0 decimal places. Here we have 1 decimal place. So our answer is going to give us 0 decimal places. So when I do the first orders, I get 20.818665. That's these 3 multiplied together. We ended up with centimeters cubed. However, we only get 2 significant figures. So this is going to be 20.8. The 8's going to round that up to 21. Here, when we add these together, the seconds just combine, so we're just in seconds. However, we have no decimal places here and 1 decimal place there. So we get no decimal places down here. The 1 does nothing to the 7. So now we're going to take 21 divided by 2387. Now when we do the division, because we have 2 sig figs and 4 sig figs, our answer can only be 2 sig figs. That gives us 0.0087, 2 sig figs, centimeters cubed per second. That might seem like a weird unit to have volume per second, but of course that could be a flow rate. All right, exact numbers. Numbers that come from definitions. In other words, 12 inches is exactly 1 foot. 60 seconds, exactly 1 minute. Numbers that can come from direct count. In other words, the number of people in a small room. Right? There's no uncertainty here. You know exactly how many are there. So conversions that come from statements of equality, that's what these two are. As long as they're in the same system, they are exact values. Or if it's a count, a certain count, we know exactly how many things are there. You will assume they have an infinite number of significant figures. So when we do calculations, it will not have an effect on your sig figs. For instance, if I take 36.00 inches and I convert that into feet, the actual value here has no impact on my sig figs. Only the measurement will determine the number of sig figs. So if I have 4 significant figures in my measurement and I multiply it by an exact conversion factor, so we're in the same system here, that means I'm going to have 4 significant figures in my final value. Okay, so 36.00 has 4 sig figs. The conversion is exact, and so our answer will have 4 sig figs. All right, for the following calculation, give your answer a correct number of sig figs. So once again, we have 3 sig figs times 5 sig figs. That means we're going to have 3 sig figs in our numerator. We have 2.234 places here, or excuse me, 3 decimal places and 2 decimal places. So when we do the subtraction, our answer will be in 2 decimal places. And so we have 178, 3 sig figs. The 8 would round that up to 179. And we have 1.18, right? Because we get 2 places after the decimal. So we'll have 1.18. So we're going to take 179 divided by 1.18. That means we get 3 sig figs. And so we have centimeters squared on top. Centimeters minus centimeters gives us just centimeters on the bottom. Centimeters squared divided by centimeters is going to give us centimeters as an answer. So we get 3 sig figs, 151, and centimeters as our final answer. All right. The next topic we want to look at is dimensional analysis, also referred to as factor label method. Not all calculations are going to use a specific equation. In that case, we can use the dimensions, the units, to analyze the problem. For instance, conversion factors, they're fraction formed from valid equality or equivalence between units. So if we go back and look at 12 inches or in a foot, we can set that up as a fraction and use it to cancel out units. This way we can change units without actually changing the value of our answer. The actual numbers may change, but overall it's the same because we're simply multiplying by 1. So in other words, we'll have a given quantity, we'll multiply that by some sort of conversion factor, and that will give us a desired quantity. An example, converting a person's height from 68 inches to centimeters. So we'll start with the facts. That is 2.54 centimeters is exactly 1 inch. Now for crossing systems from English to metric or metric to English, it won't always be exact. In length, it happens to be a defined exact amount when we use 2.54 centimeters equal to 1 inch. In essence, we'll be dividing both sides by 1 inch or by 2.54 centimeters, which either way gives us 1. So 2.5 centimeters per inch is equal to 1 inch over 1 inch. Here we can see the inches would cancel out, which means we have 1. We're literally multiplying our answer by 1. If it's 2.54 centimeters divided by 2.54 centimeters, equaling 1 inch over 2.5 centimeters, once again, centimeters cancel out, which means that conversion factor would be equal to 1. The units will cancel, leaving the ratio that equals us to 1, which means if we use the fact that units behave as numbers do in mathematical operations, we'll get things to cancel out the way we want, leaving us with the units we want. That, in essence, is dimensional analysis. Again, the given quantity times the conversion factor would give the desired quantity. So if we started with 68.0 inches, we multiply that by our conversion factor, 2.54 centimeters per inch. Our inches here will cancel out, and we'll get 173 centimeters with 3 sig figs. The dimensional analysis can tell us when we have the wrong arithmetic. So let's say we flipped that and we did it wrong. We have 68 inches times 1 inch over 2.54. Notice our inches do not cancel out and we're left with inches squared per centimeter. So dimensional analysis is basically using the units to make sure you have the correct answer. This means that you could actually end up with correct answers without understanding the formulas. And that's okay. If you're slick enough and smart enough and intelligent enough to take advantage of those units to get an answer you wouldn't have had a shot at, I say go for it, right? That is part of reasoning, logical reasoning. It's a skill set. You can definitely hone that in and take advantage of that. So let's use dimensional analysis. We're going to convert 0.097 meters to millimeters. Now we're in the same system. So here, the values are going to be exact and it's not going to impact your sig figs. The relationship is 1 millimeter is equal to 1 times 10 to the negative 3 meters. You could also say that 1,000 millimeters is equal to 1 meter. It will work either way, okay? Once again, you can make two conversion factors. We could say 1 millimeter over 10 to the negative 3 meters, or 10 to the 3 meters over millimeters. What I want to do is get what I want by itself and on top. So if I'm converting 0.097 meters to millimeters, then I'm going to want millimeters on the top, right? Since I'm going from meters to millimeters, we'll use the one on the left where we have the millimeters on top. So we have 0.097 meters times 1 millimeter divided by 1 times 10 to the negative 3 meters. Meters will cancel out. We can run that through our calculator and we get 97 centimeters. All right, learning check. Convert 3.5 meters cubed to centimeters cubed. Your basic equality here would be 1 centimeter is equal to 0.01 meters. I'm going to pause here so you can get a chance to work it out and get ahead of me. Now you're going to cube both sides. So the units and the numbers. 1 centimeter cubed is equal to 0.01 meter cubed. Running that through my calculator, I get 1 centimeter cubed is equal to 1 times 10 to the negative 6 meters cubed. We can now make two conversion factors, right, which is what we've done so far. And now we'll take our 3.5 meters cubed. Since I want to get rid of the meters cubed, I put that in the denominator, 1 times 10 to the negative 6. 1 centimeter then would be cubed would be on top. Meters cubed cancels out. And I get 3.5 times 10 to the 6 centimeters cubed. Now notice I changed the sign because I brought the 10 to the negative 6. There's 10 to the negative 6 from the denominator up to the top. You might want to review your exponent rules here. This would be 3.5 times 10 to the 0. 0 minus a negative 6 would give me a positive 6. Again, if you need help with that, you can either check some math tutorial there if you want, or come just visit me in an office hour. I'd go over that for you if you need to. Non-metric to metric units. Whenever we convert speed of light from 3.0 times 10 to the 8 meters a second to miles per hour, we're going to use our dimensional analysis yet again. 1 minute is equal to 60 seconds. 60 minutes is equal to an hour. 1 kilometer is equal to 1,000 meters. 1 mile is equal to 1.609 kilometers. So here we can take 3 times 10 to the 8th meters per second. We can cancel our seconds out, 60 seconds in a minute. We can also cancel our minutes out and go 60 minutes in an hour. So seconds will cancel out here, minutes will cancel out there. When I run that through my calculator, I get 1.08 times 10 to the 12 meters per hour. But we want miles per hour. So next, I'm going to take 1.08 times 10 to the 12 meters per hour, multiply that by 1 kilometer per 1,000 meters, and then 1 mile per 1.609 kilometers. Here, my meters will cancel out. Second, my kilometers will cancel out. I'm now in miles per hour. When I run that through my calculator, I get 6.71 times 10 to the 8th miles per hour. All right, your turn. The Honda Insight hybrid electric car has a gas mileage rating of 56 miles to the gallon. What is this rating expressed in units of kilometers per liter? Looks like we might be going to Ireland. All right, there are your options. So A, B, C, D, or E. Give you a pause here. You could have worked this problem out. Hopefully you got 24 kilometers per liter. Now, here's how I work it out. We got 56 miles per gallon. I want to get rid of gallons. So 1 gallon over 3.784 liters. And then I want to get rid of miles. I want that in kilometers. So I'm going to multiply that by 1.609 kilometers per mile. Here I can see my gallons will cancel out, leaving me liters. And here I can see the miles will cancel out, leaving me kilometers. All right. The volume of a basketball is 433.5 inches cubed. Convert this to millimeters cubed. And there are your options. And I'll pause here. You can hit pause on the video, work the problem out, hit play, and hopefully you got B, 7.104 times 10 to the 6th millimeters cubed. Here's how it goes. We have 433.5 inches cubed times 2.54 centimeters cubed per inch cubed Inches cubed would cancel out. Then we have meters cubed per 100 centimeters cubed. So here our centimeters and centimeters cancel out along with our cubed again. And then we have 1,000 millimeters per meter. Also needs to be cubed. So our cubes will cancel out. Meters will cancel out with meters. Will be in millimeters. And that's how we got 7.104 times 10 to the 6th. All right. Next up is density. All right, density is the ratio of an object's mass to its volume. Mathematically, it'd simply be D equals M over V. It is an intensive property, therefore it's not size dependent, it is size independent. It's determined by taking the ratio of two of the extensive properties, and we saw that earlier when we talked about the difference between intensive and extensive. Frequently, the ratio of two size-dependent properties leads to an independent property. So this is very often the case. If we take two extensive properties and divide them, we end up with an independent property. Okay? The sample size cancels, leaving us the intensive property. The units here will be grams per milliliter or grams per centimeter cubed. You're probably pretty familiar with density. This is usually plug and chug for us at this stage. A student weighs a piece of gold that has a volume of 11.02 centimeters cubed of gold. So in other words, we have a volume of centimeters cubed, 11.02. She finds the mass to be 212 grams. What is the density of the gold? So again, typical plug and chug problems for us. Density is equal to mass over volume. So I'm going to take 212 grams. I'm going to divide that by 11.02 centimeters cubed. Here my units are not going to cancel out, but I'm going to end up with a unit for density. I do need to concern myself with sig figs. I have 212 grams, that's 3 sig figs. 11.2 gives me 11.02 gives me 4 sig figs. That means our answer can only have 3 significant figures. So when I plug that through my calculator with rounding, I get 19.3 grams per centimeters cubed. Now, another student has a piece of gold with a volume of 1.00 centimeters cubed. What does it weigh? Now, if gold is gold, then it should be 19.3 grams as well, because now the density is 19.3 grams per centimeters cubed. We have 1 cubic centimeter, and so we would cancel those out to get 19.3. Now, what if it were 2 centimeters cubed in volume? Well, again, if the density is 19.3 grams per centimeters cubed, it should be 38.6 grams. All right. For density, most substances expand slightly when heated. In other words, you have the same mass, but because the volume is growing, we get a larger volume. That means it's going to be less dense. So density decreases slightly as temperature increases. Of course, that's how an air balloon works, right? Liquids and solids, change here is going to be very small, which means we can ignore except in very precise calculations. And of course, density is useful to transfer between mass and volume of substance. All right. Glass has a density of 2.2 grams per centimeter cubed. What is the volume occupied by 35 grams of glass? So here we're going to have volume is equal to mass over density. That's equal to 35 grams divided by 2.2 grams per centimeters cubed. That's going to give me 16 grams. And again, keeping track of our sig figs here, we got 2 in the top, 2 in the bottom, which means we get 2 for our answer. What is the mass of 400 centimeter cubed of glass? So here we're going to take mass is equal to density times volume. That's going to equal 2.2 times 400. Here we have 2 sig figs times 3 sig figs. That's going to give us 2 sig figs as our answer. And we get 8.8 times 10 to the 2 centimeters cubed. Again, if I'm going a little fast, I apologize. But this should be relatively information you're used to using. So if you need to rewind and try again, go for it. But again, the expectation here in Chem 150 is you've seen density a few times already. If you're struggling with it, again, don't hesitate. I know the assumption for the course is that you've seen this stuff before, but if it is new material for you, don't shy away. Come visit me, check it out. Go, you can always go back, rewind, look at it over and over again. Not that you want to spend a lot of time on it, but if you feel like you're struggling, come get help. Don't hesitate. It's no big deal. All right. I should say it's no big deal that you come get help. It is a big deal. You need to understand the information, right? Practice, practice, practice. All right, titanium is a metal used to make artificial joints. It has a density of 4.54 grams per centimeter cubed. What volume will a titanium hip joint occupy if its mass is 205 grams? So here are your options. And if you needed to pause to work the problem out, it's not a problem. Once you hit play again, here's your answer. 4.51 times 10 to the 1 centimeters cubed. All right, and so here your volume is equal to 205 grams. We're going to divide that by the 4.54 grams per centimeters cubed. And of course, the calculator should give us 45.154. But of course, we get 3 sig figs. So you might have 4.52 times 10 to the 1 or even 452. All right, a sample of zinc metal. Density is equal to this, was submerged in a graduated cylinder containing water. The water level rose from 162.5 centimeters cubed to 186.0 centimeters cubed when the sample was submerged. How many grams did the sample weigh? And there are your options. Give you a little pause. And hopefully you got 168 times 10 to the 2 grams. So here we took mass is equal to density times volume. They gave us a density. Right? So the first thing we're going to do is figure out our volume. So we have a volume of 23.5. And now we can plug that in, right? So mass would be equal to 7.14 times the density, which is what they gave us. We're going to multiply that by the 23.5, which is the difference in the water. Centimeters will cancel out here. We'll have grams. And we get 3 sig figs. All right, so this segment is going a little long. And that's because these topics are all really related to each other. So I hate that I've gone well over the 20-minute mark, but we just have one topic left, which is specific gravity. And then we'll just talk a little bit about measurements in general. So specific gravity is the ratio of density of a substance versus the density of water. So specific gravity then would be the density of the substance divided by density of water at the same temperature. Now specific gravity becomes unitless. Okay, and again, it's a way to avoid having to tabulate densities in all sorts of different units. So it also removes the temperature dependency of density. Here we go. Concentrated sulfuric acid is sold in bottles with a label that states that the specific gravity at 25 degrees C is 1.84. The density of water at 25 degrees C is 0.995 grams per centimeters cubed. How many cubic centimeters of sulfuric acid will weigh 5.55 kilograms? So how do we figure that out? Well, one way, we know 5.55 kilograms of sulfuric acid would equal how many cubic centimeters of sulfuric acid? Right? That's pretty much what they're asking us. So we'll take the density of sulfuric acid is equal to specific gravity times density of water. So we know the density of sulfuric acid then would equal 1.84 times 0.995 grams. Now remember, the specific gravity was unitless. The density of water would be equal to 0.995 with the grams per centimeters cubed. That's going to give us 1.83. Now we're going to keep those units, right? So even though the specific gravity was unitless, the density is not. And that means the density of sulfuric acid then would be mass over density. We know the density is 1.83 grams per centimeters cubed. We know that the mass we're given is 5.55 kilograms, which would be 10 to the 3 grams. So now grams will cancel out. Our centimeters cubed will move from the denominator of the denominator up to be the numerator, which means we get 3.03 times 10 to the 3 centimeters cubed. So you might have to go through that one a little bit. Take your time with it. All right. Liquid hydrogen has a specific gravity of 7.08 times 10 to the negative 2. If the density of water is 1.05 grams per centimeters cubed at the same temperature, what is the mass of hydrogen in a tank having a volume of 36.9 meters cubed? All right, here are your options. And I'll pause here. You can work your way through it before I start giving answers or even my analysis. All right, so hopefully, if we take our time and look at this, we have liquid hydrogen has a specific gravity of this. If the density of water is that at the same temperature, what is the mass of hydrogen in a tank having a volume of that? So we know we have the density of water is this, the specific gravity is that, right? We want to get then the density of the liquid hydrogen at whatever temperature this is. All right, so we'll do that. And then once we have the density of the liquid hydrogen, we can use the volume here to figure out the mass. I'll pause again and let you try to calculate that out before I work it out on the slide. Hopefully you got 2.74 times 10 to the 6th. So here's how we did it. Density of sulfuric acid is equal to specific gravity of sulfuric acid times the density of water. So we're going to take the 7.08 times 10 to the negative 2, multiply it by the 1.05 grams per centimeter cubed. That gives us 7.43 times 10 to the negative 2 grams per centimeter cubed. Now once we have that density, we can use the volume to calculate the mass. And so we'll take the 7.43 times 10 to the negative 2, multiply that by the 3.69. Of course, we have to switch to get rid of the meters here because they gave us meters up there. Whoops, we'll make those meters cancel out and take, let's see, 7.43 times 10 to the negative 2 times 36.9, excuse me, not 3, times